If you've been following along with my problem-solving videos, you'll have seen a number where I say add a reaction to your reaction map. In this case, for this abbreviated organic chemistry course, I'm not doing an entire reaction map. I'm just I made for you a list of the reactions that we've covered up to this point, and most of them that we're covering for the class, and I've compiled them into a reaction list showing you all of these reactions that we've done through chapter 18 or 19. So the first reaction you covered was a combustion reaction, where you take an organic molecule with some number of carbons, hydrogens, and oxygens, react it with oxygen, and make carbon dioxide and water. It's a very common type of reaction in our world, as well as our cells do this to help get us energy. They do it in a whole lot of steps, but I made a generic formula for it, and you can see how things tie together. There are N carbons that you start with and N carbon dioxide that you end up with. With hydrogen, you start with M. They make water molecules. It takes 2 for every water molecule, so there's the M over 2. In order to make this many carbon dioxide and water, you need N times 2 oxygen. So here's the 2N oxygen. You also need M over 2 oxygen. There's the M over 2 that goes with that 1, implied 1 on oxygen. And if you already have some oxygen to start with, you don't need those, so we subtract P. Our oxygen molecules come as pairs of oxygen, so we divide the total number of oxygen we need by 2. And then if it comes out to, say, 3/2, we double everything to get whole numbers. So you could figure that out, or you can just balance it for each one you do. More interesting for our purposes is the rest of this list of reactions, where this lists every reaction we've covered so far, and maybe 1 or 2 that you haven't seen yet. With alkanes, besides combustion, we only saw 1 reaction. Alkanes are not very reactive, but you can remove hydrogen and put on halogens. So you need to remember and add to your notes what X is. X can be fluorine, chlorine, bromine, or iodine. Well, let's look at how you use this sort of reaction list. First thing to do is look at, well, the thing you want to figure out is what changes. And one way to do that is to mark what stays the same. R1 is the same in both. R2 is the same in both. All these C's and single bonds are the same. The H's down below are the same. The H on the top right and the single bond is the same. The single bond on the top left is the same. There's one thing that goes away. This H goes away. There's one thing that appears. this X appears. If we look at the next molecule, almost everything stays the same. Once again, R1, everything all the way across to R2, these single bonds. But now we have added 3 more halogens. This is how you make things like Teflon or chlorofluorocarbons that hurt the ozone layer, and chlorofluorocarbons, bigger ones that have still been used, are still used in refrigerants, although we're phasing them out, and ones that are used in places like military bases to put out fires. And all these chlorofluorocarbons, these bigger ones that aren't going up and destroying the ozone layer, are sticking around in our water supply. And so now we're facing the task of how do we remove these very stable molecules from the water supply, or how do we break the halogens off of them and turn them into harmless halide ions. And this is a major area of research that the Department of Defense is funding in order to clean up water supplies around the military bases where they've put a lot of these into the environment. Let's look at the next reaction. You can probably do this yourself now, and that's a good idea to pause the video and try it, but identify what's the same. R1, R2, R3, on this alkene, all the same. Single bonds in, all the same. Single bond going across, the same. The double bond disappears, and a single bond up to an X appears. We're missing some parts though. We added HX, and we just see an X appearing. We have to remember our implied elements. There's an H here that's not drawn, and over here as well, but that just makes 3 bonds to this carbon. There should be a 4th. There's an H that gets added that wasn't represented in this line angle generic structure. So learning to see the H's in line angle structures is a helpful thing, even though they're not written. Okay, you can go through the same process with the next 2. I'm going to skip over to the right side to our alcohol reactions. What's the same there? With this alcohol becoming an aldehyde, R1's the same, as is that single bond, as is single bond, as is O. We can go further to the carboxylic acid. R1, single bond, half the double bond, and O, all the same. Now we can start finding the differences. We lose an H from the alcohol. We gain a double bond to the O in the aldehyde. In the carboxylic acid, we've still got the double bond to the O, but now we've got a single bond OH completing the carboxylic acid group. Don't forget the implied hydrogen. Here, there have to be 2 hydrogen, whereas in the aldehyde, we're down to 1. So there's been a hydrogen lost, and as we go to the carboxylic acid, that hydrogen that remained goes away and is replaced by an OH group. This all happens with our primary alcohol here. Here we have a secondary alcohol. And we can see what happens when it is oxidized. R1 and R2 stay the same. The carbon in the center stays the same. One bond and the O are the same. The H disappears. And a double bond forms there. But that's not all that happens. There's one implicit hydrogen here, and it goes away, so we've lost H2. And in these reduction reactions, which is what all of these are, alcohol to aldehyde, aldehyde to carboxylic, they're not reduction reactions. In these oxidation reactions, we are adding oxygen, more bonds to oxygen. We're taking off hydrogen. So in each of these, we're taking off an H2 while we add an extra bond to oxygen. And these are oxidation reactions. You can write over the arrows, you can write common reagents that are needed to make these reactions happen. I've not done it on all of them, but on many I've written at least part of it. These arrows coming off, most of these reactions are reversible and can go backwards. This first alkane reaction does not go backwards easily. It's actually very hard to make it go backwards. So I didn't put a reverse arrow. But here, I've got a reverse arrow. We can go from a halogenated hydrocarbon, an alkyl halide, or a haloalkane, to an alkene by removing HX. And that arrow coming off shows that we're removing HX as we go from right to left. Let's show how we'd use this reaction map in solving a problem. So here I have a wax molecule. Very long hydrocarbon chains, very nonpolar, a somewhat polar group in the middle, reacting with acid. Now, in most of your problems, it'll tell you what the products will be. If we didn't know the products, we could still look on our map or our list of reactions and look for an ester, and there's an ester. An ester can react with this left-pointing arrow to make a carboxylic acid and, the arrow down, an alcohol coming out of it. So we just need to relate this reaction up here to this molecule down here. So one thing we would need to make this reaction happen is we would need water. So H2SO4, let's also add some water, do this reaction in water. Let's compare this molecule to our generic ester. We've got a carbonyl oxygen, single bonded to another oxygen, and that looks just like our ester up here. That means that our R2 is everything connected to the single bonded oxygen. So this whole long chain I can just replace with R2. And on the other side, R1 I can replace with this whole long chain. And I'm going to do that. Replace the chain on the left with R1, the chain on the right with R2. Now I can focus in on just the part that's reacting. And I go up here, and this part that reacts splits up. A carbonyl goes with R1, and that's what I've done here. And then I add an OH to it, like I've done here. Let's go with the alcohol. We've got our R2, and along with the R2 comes an OH. And that's what I've added to my R2 down here. So just by comparing the pieces of my original molecule, of my generic molecule, to my reacting specific molecule, I can simplify it down to just the parts that are changing. The part in yellow here, the part in yellow here. And that's a process you can follow with a little practice for every reaction that we do in this class. You can make yourself a list of reactions, or you can copy down mine and solve every reaction problem that we will have in this class.